previous lecture described the difference between structure and behavior. That is, structure defines a collection of instantiated logic elements and the way that those instantiated elements are interconnected. And it serves as a level of the design hierarchy. Behavior, on the other hand, defines the Boolean and or memory characteristics of a logic element. However, neither of the design approaches we've covered so far, namely schematics and Boolean algebra, are practical for large-scale designs. In this lecture, I'll introduce Hardware Description Language, or HDL, which is a type of high-level language that provides a way to describe both logic structure and logic behavior without having to draw schematics or write Boolean logic or truth tables. HDL is a high-level language. Actually, it's a set of high-level languages, like Java and Python, but HDLs are different in that they have concurrent semantics. That means that the code, HDL code, is composed of statements that execute simultaneously, as opposed to traditional languages that you've used so far, where only one statement is executed at any time. There are many HDLs, but the two most common are Vhdl and Verilog. Vhdl was the first HDL, developed in 1981 by the Department of Defense as a way to precisely deliver chip specifications and requirements to defense contractors who are making custom chips. VHDL is an acronym that stands for VISIC, Hardware Description Language, where VISIC is also an acronym that stands for Very High Speed Integrated Circuit. Verilog, and its current form is called SystemVerilog, is a slightly newer HDL developed by the private sector in 1984. VHDL is still popular because it has a very verbose and self-documenting syntax. And if you looked at VHDL, it bears a lot of similarity to a lineage of languages that includes Pascal and Ada. Verilog and its current specification, SystemVerilog, and by the way, I'll use Verilog and SystemVerilog interchangeably throughout the lectures, but when I say Verilog, I'm really referring to SystemVerilog. So SystemVerilog is a slightly newer HDL developed in the private sector in 1984. It has sparser and a more concise syntax, closer to Python and Java. But otherwise, it has the same objective and functionality as VHDL. I actually switched this course from VHDL to Verilog around 2014 because of Verilog's more familiar syntax and because Verilog seemed to be gaining an edge over VHDL, at least in industry, not necessarily in academia. However, if you know one of these two languages, the other is very easy to pick up. HDLs were originally designed to describe logic behavior and structure in a more abstract way than using Boolean logic, truth tables, and schematics. And soon after the languages were developed, there were simulators developed that allowed for verifying the correctness of designs in the HDL. Eventually, a new type of tool was designed that could synthesize HDL designs into actual hardware in the form of either mask sets that could be shipped for fabrication as custom chips, or as gate level schematics and a mapping, corresponding mapping of gates to slots on a reconfigurable logic device called an FPGA. Both Vhdl and SystemVerilog directly capture the concepts of abstraction, hierarchy, and regularity by way of explicitly declared design elements that can be used and reused and even packaged in libraries to build up increasingly large-scale designs in a very natural way. In SystemVerilog, these logic elements or reusable designs are called modules. And in VHDL, they're called entities, but this is the same thing. A module, an entity, a design a logic element, these are all the same thing, same concept. A SystemVerilog module defines an explicit list of inputs and outputs. Internally, a module might contain structural HDL, behavioral HDL, or a combination of both. Structural HDL is an HDL description of a schematic. So it's equivalent to drawing a block diagram, but it's written in a high-level language. And actually, it sort of resembles instantiating classes into objects as you do in Java. And the modules are interconnected with wires, where the wires are actually declared as sort of internal. They appear to be internal local variables like you would have in Java. Behavioral HDL defines how outputs are derived from inputs using statements containing operators, conditionals, loops, and memories. So similar concepts to what you're already familiar with from Java and possibly Python. Usually, each Verilog module is stored in its own file. Now, this isn't required, but it's a very common convention. So one file per module. The file is typically named with the same name as the module with the file extension SV. So, for example, if we have a module named example, we'll store it in a file called example.sv. The module file might begin with compiler directives similar to a pound include and pound define in C++. But after that, you'll generally find the module line. Now in this class, we don't use compiler directives very often, so generally the first line of your module file will be the module line. The module line begins with the word module, followed by the name of the module and an open parenthesis, and the list of inputs and outputs, followed by a closing parenthesis, and then a semicolon. Don't forget the semicolon. The input and output list is separated by commas. This is also called the port list, since the inputs and outputs are ports to which you connect signals and any design that instantiates this module, that uses this module in building up its design. Inputs and outputs can appear in any order, although by convention, inputs are usually listed first. The keyword input and output are type modifiers, while the keyword logic is a data type. The logic type can take on values 1, 0, X, or Z. Now there are other types in SystemVerilog, such as the type bit, that can only take values 0 and 1, but we will only use the logic type in this class. Notice that the inputs B and C don't have a type modifier. Because of this, the compiler will use the last specified type and type modifier for these variables, making B and C input logics as well. After the module line, we have an assign statement, which is also called a continuous assignment statement or a concurrent assignment statement. So sometimes I'll refer to it as an assign statement or a concurrent assignment statement. This statement executes concurrently, meaning that the value on the left-hand side of the assign statement or the left-hand side of the equal sign in the assign statement will update automatically when any of the values on the right-hand side of the equal side change state, change values. In this case, the assignment statement is driving the output y using a simple Boolean expression. The tilde denotes a complement operation, the ampersand an and operation, and the vertical bar an or operation. And so these are already familiar to you from Java and C++, except possibly the tilde, because you may be used to using a explanation point to denote a logical not. But Verilog uses the tilde. The statement is ended with a semicolon, which is also familiar. The module is ended with the end module keyword, but notice that there is no semicolon after end module. When this module is simulated, or any module for that matter, the results are generally shown using a timing diagram, much like what you see on an oscilloscope or logic analyzer, if you've seen those, bench instruments, essentially. The timing diagram is a plot where the horizontal axis is time, and the vertical axis represents the logic level, but you can also think of it as the voltage level. So it shows a 0 and a 1 level. Multiple signals can be plotted and tracked on a timing diagram, and they're listed vertically, although the one of the confusing parts of a timing diagram is that it is not obvious by looking at the timing diagram which of the signals shown are inputs and which are outputs relative to whatever level of the hierarchy you're testing. The timing diagram shows the value or the state of A, B, and C changing, where at least one of these three changes every 100 nanoseconds, and over the course of 800 nanoseconds, these three values cycle through the sequence of all possible combinations according to a counting sequence from 000 to 111. For each state of A, B, and C, the corresponding value y is plotted. So in other words, A, B, and C are the inputs and y is the output. The purpose of the timing diagram is to check and potentially debug the functionality of this module. For modules with more inputs and output bits, it's not practical to cycle through every possible input combination, nor would it be possible to verify the correctness of the module by just looking at the timing diagram through a visual inspection. But there's ways to solve this problem that we'll describe later. The module is responsible for setting the value of y from its assigned statement. But the question is, what's driving the values of A, B, and C? In other words, the module is setting y. Who's setting A, B, and C? Well, these values must be getting set from an unseen entity, such as from another module that has instantiated the example module, or through a series of simulator commands that are forcing the A, B, and C inputs. Now, please assume that there's another design there that's driving the A, B, and C signals that's not being shown here. We'll return to this idea soon. If this module were synthesized, the synthesizer might generate a gate level structure corresponding to this module, as shown here. Although there's many possible ways that this design could be synthesized into a gate level structural design that has an equivalent behavior. And since we didn't specify a timing specification for this module, any equivalent logic implementation that matches the behavioral specification given in this module are acceptable regardless of their performance. So in other words, there are many ways that this module can be converted down to the gate level by a synthesizer. Verilog follows similar syntax rules as does Java and C++. It's a case-sensitive language. Identifiers such as inputs and outputs and internal connections cannot start with numbers. Why is that important? Well, because sometimes in digital logic, it can be tempting to use names that start with numbers, such as 2mux for a 2-input mux. White space is ignored, and comments follow the same rules as Java and in C, in which line comments start with // 2 forward slashes, and block comments start with a /* asterisk and end with an asterisk /. One of the most important things to understand about SystemVerilog is the way in which named wires that connect instanced modules in a structural design effectively will become renamed inside of the instantiated modules by way of its input and output port map. So this concept is similar to the idea of actual arguments versus formal arguments in any high-level language. So consider the following two module definitions for and3 and myDesign. Within myDesign, the and3 module is instance similar to how an object is created from a class in Java where you specify and3 followed by the instance name and gate, or that would be equivalent to an object name, followed by the port mapping, where the port names begin with a dot. Those are the formal port names as defined within the and3 module. And the local connections, that is the wires, the signals within the myDesign that you want to connect to each of the ports are listed inside of parentheses. The signals that we connect to these ports are declared as type logic, and notice that they are not in the port list for myDesign, so they are internal signals. Here's a slightly more complex example involving three modules. And3, INV, which is short for inverter or invert, and NAND3. NAND3 is the top-level design because it contains one instance of both of the other modules. In this case, the NAND3 module has top-level inputs A, B, C, and Y, shown here, and internal signal N1, which is declared internally, and then one and3 and one INV are instanced. Now, we could instance more if we wanted to, but in this case we just instance one example of both, each with its own named input and output ports. The port mapping of the and3 module will connect the inputs of NAND3 to the inputs of and3, and the output of and3 Y to the internal signal N1. The port mapping of the INV instance connects the internal signal N1 to its input A and connects its output Y to the output Y of the top-level NAND3 module. Inputs, outputs, and internal signals can be declared as having multiple bits, as opposed to 1 as I've shown in the examples so far. To do this, you specify the number of bits before the name of the signal, which makes it different than Java and Python style syntax. And also, instead of just giving the number of bits, you have to use a somewhat arcane syntax where you subtract 1 from the number of bits, followed by a colon, and then followed by a 0. This way, you're providing a range of bit enumerations from most significant to least significant. So for example, 3:0 would be a 4-bit signal because it includes bits 3, 2, 1, and 0. Logical operations that are performed on multi-bit signals are performed on each pair of individual bits. In other words, the operation is performed between bit n of one operand and bit n of the other operand, with n ranging from bit w minus 1 to 0, where w is the width of the operands in bits. Logical operations include complement and or an XOR. SystemVerilog also supports the ternary operator, which is supported in Java and C, but is much more commonly used in SystemVerilog. The ternary operator allows an expression to evaluate to 2 possible sub-expressions, depending on the outcome of the conditional expression. The syntax is the condition, followed by a question mark, and then the expression if the condition is true, followed by a colon, and the expression if the condition is false. The ternary operators are useful for expressing the behavior of multiplexers. Since the condition acts like the select input, and the 2 expressions act like the inputs of the multiplexer. And of course, the evaluation of the entire ternary expression would be equivalent to the output of the multiplexer. Since you can nest ternary expressions, you can scale them up to create multiplexers with more than 2 inputs. In the example above, the assign statement performs the behavior of a mux with 1 line of code, as the output of y is assigned to d1 when s is 1 and d0 otherwise. Let's look at a slightly more complex example, purely behavioral module that performs the behavior of a full adder. This module has 3 inputs and 2 outputs and 2 internal signals. The internal signals stand for propagate and generate, PNG, and their state is determined by an assignment statement. There are separate assignment statements that set the 2 output signals. This creates a dependent relationship between the top 2 assigned statements and the bottom 2, although it doesn't matter what order the lines of code appear in the module. Because if the state of A or B changes, this will automatically trigger an update in both the P and the G signals, because A and B appear on the right-hand side of those assigned statements. And when P and G update, this in turn will automatically trigger updates for the S and the Cout signal, which are outputs that are listening for changes in P and G. SystemVerilog's operator precedence is exactly the same as C++, but SystemVerilog has a slightly different set of operators. SystemVerilog does not support self-assignment operations like plus equals and minus equals and times equals, but unlike C++, it supports explicit logical and arithmetic shift operations. Whereas C also supports arithmetic and logical shift operations, but it infers which one to use through the data type of the first operand. SystemVerilog also supports explicit bit widths for constant numbers. When specifying a constant number in SystemVerilog, you should specify its bit width followed by an apostrophe, followed by a base specifier, followed by the value. The base specifier is H for hexadecimal, B for binary, O for octal, and D for decimal. So for example, the value 12 apostrophe D10 would represent a binary value that begins with 8 leading zeros, because the decimal value of 10 only requires 4 bits, and then followed by 1010, which is the binary value for 10. So stated another way, the value 12 apostrophe B10 would specify the decimal value of 10 in 12 binary bits, which would be 8 zeros followed by 1010. You can also use underscores to separate different components of a constant number to improve readability. So for example, 4 apostrophe B01 underscore 10 will encode the value of 6 in a 4-bit value, and the compiler ignores the underscore, but by having the underscore in there, it signals to the designer that this 4-bit number should be logically decomposed into two 2-bit fields. SystemVerilog also supports convenient methods for manipulating binary values. Sometimes I call this bit twiddling. Individual bits from a larger value can be spliced out using square brackets. So for example, you can isolate the middle 6 bits of an 8-bit signal A, assuming A is an 8-bit signal, using the syntax A left bracket 6:1 right bracket. You can concatenate bits using curly braces. So for example, left curly brace A bracket 3:0, meaning 3 down to 0, or the 4 least significant bits of A, comma A 7:4, or 7 down to 4, bit 7 down to 4, and then right curly brace will concatenate the lower 4 bits to the upper 4 bits of A. It's basically swapping each half of the signal. You can use these concatenation expressions on either the left or the right-hand side of an assignment statement. Now this one's a little bit confusing because it also uses the curly brace. So for example, the expression left curly brace 4, left curly brace A, 7 down to 4, right curly brace would duplicate the upper 4 bits of A 4 times, giving a 16-bit result. SystemVerilog also offers reduction operators, which allow you to perform a logical operation using all the bits of the signal as inputs. So as opposed to doing a bitwise logical operation between 2 different, potentially multi-bit signals, a reduction operation takes all the bits that make up one signal and feeds them into a single gate, giving a 1-bit result. So for example, the expression ampersand A will effectively feed all 8 bits of the signal A into an 8 input AND gate, giving a 1-bit result. Reduction operators exist for AND, NAND, OR, NOR, XOR, and XNOR operations. To summarize this lecture, we discussed how to build structural SystemVerilog and how to build some behavioral SystemVerilog using the continuous assignment statement. In the next lecture, we'll cover SystemVerilog processes, which allow the designer to design more complex behaviors than what we looked at in this lecture with just the assign statement, as well as the processes also allow the designer to create test benches, and we'll also put in a little tutorial on how to use our simulator. Thank you. So consider the following 2 module definitions for and 3. Scratch that. What? And myself? What? What is that? Oh, in my design, okay. So consider the following two module definitions.